So welcome everyone to the week 10 of the tutorial of this Sobolev and partial differential equation course. My name is Shammi and I'm a research scholar at IIT Delhi, working in the field of partial differential equations. So in this week, in the video lecture, we saw that the sir discussed about the maximum principles, and after discussing the maximum principles, we eventually learned about the eigenvalue problems of eigenvalue problems. We can associate with any operator. In generally, we saw the eigenvalue problem for the Laplace operator, and then like we can again discuss the same set of problems for another operator as well. But Laplacian being the starting point where this eigenvalue problem is actually started studying for this type of differential equation operators. And this very famous problem, stum library problem, that is actually in the one-dimensional case, and that actually deals with this eigenvalue problems. So we see that and then we see about the variation characterization of eigenvalues and how we can actually we have more information about the first eigenvalue and the first associated eigenvector. So that again it turns out to be simple, and then sort of properties like that, and we have some more properties for the nodal domains, and then about the nodal domains of eigenfunctions. So in today's lecture, we will discuss maximum principle, like we see sort of another maximum principle for another type of operator, like the idea being the same, but we will see that the same techniques we can adopt to have a maximum principle for another type of operators as well. And then we will see some questions based on the eigenvalue problem. That will be planned for today. So uh, let's start today's session. So the first question, actually, we will prove a maximum principle, and the method basically through which we prove our problem is actually in literature known as the Stampacchia truncation method, and that is uh, a very no, I would say a nice approach in proving the maximum principle. So we will see how basically that method is used. So question number one. Let f in L2 of I with I'm taking I to be just the unit interval, and let U to be in H2 of I be the solution of the Dirichlet problem. And the problem is it goes like the minus U double dash plus U equal to F on I, U0 alpha, and U1 is beta. So this is it's a non-homogeneous Dirichlet problem. And then prove that for every x in I, we have minimum of alpha beta, and increment over I of F has to be less than equal to so it's like since we are able to define point-wise value in the one dimension, so we have the maximum principle in this type of point-wise sense. Actually, we can take the infimum and as well as the supremum of ux, that as well. But yeah, the point being that we can actually talk about the point as well because we are in the one dimension. So to prove this, in fact, this is actually known as the come back here. Truncation method. Since I'm taking u to be in H2 for the solution of this particular problem, what we basically have here is for any v in H not 1I, we have integration I u dash after by using the integration by paths u dash v dash plus integration of I of u v equal to integration of I of f v, and that also basically that's for all v since u is the solution. So how do we actually prove this? So the method goes like what we do, we fix any function g in P1R such that whatever it holds that g is strictly increasing on 0 to infinity, and then we have gt to be 0 for t in minus infinity to 0. So one can construct this type of function. It's like smoothing out of the function of 0 and t. So since we're also taking that supremum of f and infimum of f to be quantity, we are assuming this to be finite as well. Otherwise, like the inequalities holds trivially. So set k to be maximum of alpha, beta, and supremum of I of f. So this is the maximum of taking alpha, beta, and supremum. Again, I'm taking supremum to be finite to its infinite. The inequality holds trivially. And so like suppose that k is finite only. So we have to prove so that u has to be equal to this quantity k. So how do we show that? The method goes like we just take v equal to g of u minus k. So what is u minus k? G of u minus k is a composition function, and it is clearly whenever my since g00, this is by composition theorem. This g of u minus k is actually turns out to belongs to h1 of I And what else? We know that what is u0 is alpha and u1 is beta. So this is the boundary value of u. If I consider u0 minus k is nothing but alpha minus k, which is of course less than or equal to 0. And if I consider u1 minus k, that again turns out to be beta minus k, and that is also again less than or equal to 0. Now, putting v in, let's say, let's name this thing to be star. We get, so this will be like integration of I of u dash so before putting that, we saw that this thing holds for all v in h naught 1I. But as we see that since my this u naught minus k is less than or equal to 0 and u1 minus k is also less than 0, so when I compose g of u0 minus k, that turns out to be 0. This will give g of 0 u 0 minus k. This is actually will be 0 only, and so is g of u1 minus k is again 0. And so what basically this implies, this whole implies that v is nothing but in h naught 1. Right? So we have to ensure that v is in the right space, so I can just put it in star. It will be u dash and then v dash. So v dash is nothing by the composition. It will be g dash u minus k, and then we have another u dash and plus integration I of u into g of u minus k, and then integration I of g of f times g of u minus k. So next what we can do, we can now since this whole I can write, this is integration I of u dash square g dash u minus k, and plus integration I of so I can add and subtract k of k times g of u minus k. So when you write this u minus k, g of u minus k, integration I of f minus k, g of u minus k. So I can do this. But k being the supremum, so this whole thing f minus k is actually less than or equal to 0, and g of u minus k is always non-negative. So what this basically implies? This implies this f minus k, g times u minus k has to be less than or equal to 0, and hence the integration of the right hand side is also less than or equal to 0. So integration I of u minus k and g of u minus k is also less than or equal to 0. But we know that t times gt is always non-negative for all t in R. So when t is negative, gt is 0, and when t is positive, gt is also positive. So the product is again always positive, non-negative. So that's what we basically have. We have u minus k times g of u minus k has to be equal to 0 almost everywhere. But once that is equal to 0 almost everywhere, what this basically means, this holds because I know that for u greater than k, we have this quantity to be strictly positive, the right hand side. Basically, u minus k is positive, and then so is g of u minus k. But this basically proves that it has to be u minus k has to be less than equal to 0 almost everywhere. And thus, what basically this proves that but we know that u belongs to h2 of I. So this implies u has to be continuous. So basically, this implies u has to be less than equal to k. And so we have our result. So the lower bound follows similarly. So one can calculate the lower bound as well by like replacing u with minus u, and that will actually helps you to prove the lower bound. So moving on. So next, we are interested in this is known as the Stack's truncation method, and this is quite useful, as we'll see in the next question as well. The next problem actually discusses the eigenvalue problem for another type of operator. But we will see the ideas being the same, and we will see uh, some properties. Then how we actually follow. So let me write the second question. So question number 2 is set AUV to the integration from 0 to 1 of U dash V dash plus UV plus U1 minus U0 and then V1 minus V0. So that holds for all U and V in H101. The first thing we have to check that A is a continuous cohesive bilinear form on H101. Okay, so we'll first have to prove this is cohesive. So to prove the A to be continuous, so let us start. So if you consider the mod of AUB as well as than equal to integration 0 to 1 U dash V dash modulus as integration 0 to V U whole modulus. And then this U1 minus U0 and V1 minus V0, this can again bounded above by twice of L infinity of I U and then again twice of U of L infinity of I. So again, this whole can be written as less than equal to integration 0 to 1 U dash mod square whole square of half. And again 0 to 1 V dash mod square whole square of half. 0 to 1 mod U square whole square. Again, they're using the cautious cos. 0 to 1 mod V square whole square of half. And this is nothing but 4 times norm, no, L infinity norm of U, I. And then here we can use the L infinity embedding of the basically the H1 embedding into L infinity again in the one dimension. So we have the embedding theorem, and so this all can be written as. So again, this is we know the H1 norm is the sum of L2 norm and the L2 norm of function plus the L2 norm of the derivative of the function. So it's like it has to be less than equal to H1 norm, VH1 norm, and the same goes for the others as well. So this will actually give us this is 1 and this is again U times H1, V times H1, and then finally 4 times. There will be some constant in here. UH1 and then VH1. So this gives continuity. So once we have the continuity, the next you will search for the see for the cohesivity of our form. So cohesivity. So AUU can be written as integration 0 to 1 U dash whole square plus U square plus U1 minus U0 whole square. So AUU will be this form only. And This whole thing actually can be written as greater than or equal to 0 to 1 mod u dash square plus u square. So that one thing is non-negative being a square. And this is nothing but the h1 norm of u square. And this gives coercivity. And clearly this form is bilinear. That is not a very hard to see. So cobilinear is literally. So next, once we have this whole setup for the lax milligram, the next question is kind of obvious. So we are actually interested in getting the solution. So reduce that for every f in L2 0 1 there exists a unique u belongs to H2 0 1 satisfying AUV has to be equal to integration 0 to 1 FV for all V in H101. So actually we already have all the setup, so it's like just an application lax milligram only. But there's one more thing which I have to prove. There's U has to be in H2, so that is something we would like to prove. So by application of lax milligram lemma, clearly this F integration F to F times V over 0 1, it's a linear functional on H101, so that's not an issue. Uh, there exists a unique U belongs to H101 such that AUV has to be integration 0 to 1 FV. So we have uh, the existence, but the next thing you like to prove is the AU has to be actually in fact lying H2 as well. So in fact, what do we have? This actually AUV belongs to for all V in H naught 1 I. So this point where U1 0 terms will vanish. We have integration 0 to 1 U dash V dash. That's integration 0 to 1 UV is equal to integration 0 to 1 F times V. This is nothing but integration 0 to 1 U dash V dash equals to integration 0 to 1 F minus Q times V, and this holds for all V in H01 I. Now, what this implies, this is actually nothing but the definition of the weak derivative for U dash. And what this basically implies that U dash actually lies in nothing but H101. The definition of weak derivative. from the definite weak derivative, we have this thing. So what this basically means, this is nothing but u actually lies in H2 0 1. And actually this proves our part that finally we have u in H2 as well. So next, part 3, check that u satisfies this actually system minus u double dash plus u equal to f on 0 1, and u dash 0 is nothing but u0 minus u1, and u dash 1 is nothing but u0 minus again u1. So same thing. And if I name this to be double star, so that any solution u belongs to H2 0 1 of double star satisfies star only. So we since we already got u lies in H2 0 1, and already we know AUV is equal to 0 to 1 FV. So this was there, but we also know that since we have this holds for all V in H0 and I, so we will like use this type of idea. So what is this? This is nothing but integration 0 to 1 u dash v dash plus integration 0 to 1 u v integration 0 to 1 f times v. So now what we can finally able to write now is that uh, since I know that I took v from h naught when I, so then this boundary term, so this term vanished, but if I take v from any h101, what I can write this actually is we have the like for all v in h101 from the Lax Milgram, this is nothing but u1 minus u0 times v1 minus v0. And once that we have here, what we can do, we have like since we will next to I can like use again integration by parts here. This is minus 0 to 1 u double dash v plus u dash v and we have to evaluate these at the bounded terms only. So it's like 1 and 0, integration 0 to 1 uv equal to 0 to 1 fp. This is nothing but minus 0 to 1 minus u double dash plus u minus f times p plus u dash 1 v1 minus u dash 0 v0 equal to 0. So since we already know that we have this thing, and we also use in H2, and now we can use the idea that if V belongs to H naught 1 of I, what this will imply? This will imply that 0 to 1 minus u double dash plus u minus f times V has to be 0. That for all V, and that holds for all V in H naught 1 I. What this basically implies? This implies that since CC infinity is dense in H naught 1 I, so once that thing is there, we know like we proved the theorem in like the theorem is proved in the beginning of the week 1 or 2. And that is there, we can imply that this implies that minus u double dash plus u minus f has to be equal to 0 almost everywhere. So once we have this, coming back to our original equation, this will give us u1 dash v1 minus u dash 0 v0 to be here. And moreover, we have this thing as well. Oh, I missed this. u1 minus u0 v1 minus v0 plus u1 minus u0 into v1 minus v0 equal to 0. So we have this inequality. So now I can choose v in h1 0 1 such that v1 is 0 but v0 is non-zero. So what this will imply? This will imply v0 times minus u dash 0 minus u1 minus u0 equal to whole 0. So once that we have here, so since v0 is non-zero, this will imply u dash 0 is nothing but u0 minus u1. We have this equality as well, and similarly we can have basically we have, in fact we have u dash 1 equal to nothing but u0 minus u1. So again the same idea, choosing another test function which vanish on other boundary point. And checking that any solution of this double star is also a solution of star is actually same by just multiplying any function v in h1 and then just integrating by part. And then when just using the integration by parts, we have our result. So it's like the same idea. So it's like we can work out. I'm not going to prove this. So next part is we have to check that T is self-adjoint and compact. So to prove the T being self-adjoint, and what is T? Where T from L2 01 to L2 01 be the operator defined by TF equal to U only. for self-adjoint, I take f and g to be in L2 of I, and what I will consider TF in a product with G, right? So it's again in a product in L2I. This is nothing but integration 0 to 1 TFX into GX dx. And what is TFX? TFX is the solution of my this thing, that minus u double dash plus u. So this is nothing but so since belongs to G, we have this systems associated with F and G as well. So let's say if I name this TF to be U and TGB to be some V, then this is 0 to 1, and this U. And so what is G? G also I know that satisfy this thing order. So G will be something minus V double dash plus V dx. So TF I'm writing as U, and G is nothing but it has to satisfy the equation. So this is integration 0 to 1 minus uv double dash plus integration 0 to 1 uv. So now using integration paths, we have 0 to 1 u dash v dash plus minus uv dash from 1 to 0, integration 0 to 1 uv. And then again we are using one more times integration of paths. We have minus integration 0 to 1 u times v double dash plus u v dash, this time 1 at 0, and this is nothing minus u1 v dash 1 plus u0 v dash 0 plus integration 0 to 1 uv. And all this can be written as integration 0 to 1 u times minus v double dash plus v. And then finally we have u1 v dash 1 minus u0 v dash 0. And this is finally minus u1 v1 v dash 1 plus u0 v dash 0. So this all actually cancels out, and we are left with, and u is nothing but u was nothing but oh sorry, I did a mistake here. This is nothing but actually integration 0 to 1. So I have to transfer the derivative to u only. So my bad. So it's minus integration 0 to 1 u double dash v plus u dash v 1 to 0 plus minus u1 v dash 1 plus u1 v dash, sorry, u0 and v dash 0, and then integration 0 to 1 uv. All this can be written as integration 0 to 1 minus u double dash plus u times v, and this is nothing but u dash 1 v1 minus u dash 0 v0, so minus u1 v dash 1 and plus u0 v dash 0. So we will be done if we show this extra terms apart from the integral is 0. Then we have the self adjointness of the operator T. But if you see what is u dash 1 and u dash 0, consider u dash 1 minus u dash 1 v1 minus u dash 0 v0 minus u1 v dash 1 plus u0 v dash 0. So we can substitute the values. So u dash 1 was the u0 minus u1. It's like u0 minus u1 v1 minus, again this is the same thing. So it's like u dash 0 and v dash 0 are same only. So we can also write this in more compact form. So it's let me write it directly only. So this is nothing but u0 minus u1, and then I can take v1 minus v0 to be common. And then finally we have this v dash 1 and v dash 0 to be equal. So minus u1 minus u0, and then this is nothing but v0 minus v1. And if we like change the signs and all, it's like u0 minus u1, v1 minus v0 minus u0 minus u1, and then we have v1 minus v0. And so this is about 0 only. So thus we have basically integration 0 to 1 tf g is nothing but equal to integration 0 to 1 f times tg. So this implies t is self-adjoint. And clearly t is compact, as tf belongs to H201, and H201 is actually compact in N201. So once that is there, we have this compactness. So I think we have to do there. Finally, we have a next part. So part 5. Show that if f is non-negative almost everywhere on 0, 1, then u, which is nothing but t over f, is also non-negative on 0, 1. So it's like a pointwise kind of thing, but we see that u is in H2, it's again a continuous function, so almost everywhere is replaced by a everywhere inequality. So to prove this, actually we actually usually choose a special functions, and once we have this choosing special function, we can plug in the Week's equation, and with the help of that, we will able to prove this part. So how do we do that? So again, we use this stem packet truncation method. So we'll fix when G in even R such that G1, the first thing is this GT is 0 in minus infinity to 0. Second thing is GT is strictly increasing on 0 to infinity. Now taking b equal to g of minus u, in we have to take this in this equality where the I know that my u satisfy this this thing. So using this, we have let me mention that to be something. I think that was star only. So this star only. Uh, um, yeah, let me mention it to be star only. We get a u times g of minus u equal to integration 0 to 1 f times g of minus u, right? So I know that f is almost everywhere non-negative and g is again a non-negative function. This whole integral is also non-negative. Makes sense. My f is non-negative and my g is also non-negative. But if you try to see that this aug of minus u is nothing but integration 0 to 1 u dash, and then we have to take the derivative of gu. So there will be g dash of minus u, and then this is minus u dash plus integration 0 to 1 uh, u times g of minus u. And finally, we have this boundary term as well. So it's like plus u1 minus u0 and then v1 minus v0, but v1 is nothing but this thing, so g of minus u1 minus g of minus u of 0. So since g is non-increasing, um, all of this actually, since g dash is strictly increasing, the g dash has to be non-negative and mind this a u dash square. So this, let me write this minus integration 0 to 1 u dash whole square, and then we have g dash of minus u. So since u dash square is this non-negative, and again g dash is strictly increasing, g dash is again non-negative. So this integral is negative only, and then we have this I can write as minus 0 to 1 minus u g of minus u is just, I know that t times gt is again non-negative, so will we lose this thing? And this is nothing but u1 minus u0, and this is g of minus u1, g of minus u0. So again, I know that g is it's a non-decreasing function. So if u1 is greater than u0, so we got if u1 is greater than u0, since g is non-decreasing, it's like increasing type of thing. So this will imply minus u1 minus u behavior. And what this will imply, since the non-decreasing or increasing, if you say this will be g of minus u1 will be here and g of minus u0 will be here. So basically this will imply this will have a negative sign here. And so is the case because of symmetry, I can use the other side as well. So this will give, this will have a, this will be a, this quantity will be a non-positive quantity. And this is also non-positive quantity. So this whole thing has to be less than equal to minus times integration 0 to 1 minus u g of minus u, and again that is non-negative. Again, we have this G to be increasing thing. So we can again write this as less than equal to 0 because we know that TGT is always non-negative. Right, when T is negative, it's 0, and T is positive, it's always non-negative. And so ultimately we have this A of two. Also, we have this thing to be greater than equal to 0 since AU of G minus U is greater than equal to 0. So we saw that, and that is there. So this actually implies integration 0 to 1 minus U G of minus U dx is 0 only. But as this thing is there, this actually implies minus U times G of minus U has to be 0 almost everywhere. But as we know, but as we know that when this is 0 only if when my U is this holds if and only minus U is less than equal to 0, and thus this implies U has to be less than equal to 0 almost everywhere. But U is continuous, so this implies U has to be greater than equal to everywhere only. So this gives basically that whenever my F is non-negative, my TF is also non-negative. So next, part 6. Check that TF times F in L2 is always non-negative for all F in L2 of 0, 1. So clearly this is actually direct consequence of part 5. We know that when F is greater than equal to 0, this implies my TF is also almost everywhere greater than equal to 0. And likewise, we can similarly reduce that when my F is if you use so F we can replace F with minus F, and we have reduced the same thing that when F is less than equal to 0, this will imply that TF is also less than equal to 0. So what this basically implies that if we consider TF comma F L2 now, so this is actually 0 to 1 TF times F, but then this can be written as the positive part minus the negative part, and then the same goes here. But since TF plus and F minus cannot have a common support unless there is 0, so this actually will give me nothing but 0 to F. TF positive part of TF times F positive part plus 0 to 1 TF negative part into F into negative part, and this is almost equal to 0. So that actually proves our part 6. Okay, so far so good. Finally, the part 7. So for part 7, what do we have to do? We have to prove that determine the eigenvalue of this operator T. So one thing that this eigenvalue thing, that since my TF is compact, it's not not invertible. So like that eigenvalue is zero. And we are like for timing, we are not considering that. We're considering the non-zero eigenvalues. So that 1 by lambda be the eigenvalue of t, and u be the corresponding function. Then minus u double dash plus u equal to lambda u. So this is, we know that, and moreover, we have u dash 0 is nothing but u0 minus u1, and u dash 1 is nothing but u0 minus u1. So first of all, we can see that if I consider a u u, so it's like integration by like multiplying with u. Ultimately, we have, since boundary condition will vanish, so there is nothing but lambda integration 0 to 1 u square, and we have seen that it is when we are proving coercivity, we have proved that this AUU actually has to be greater than the integral of u square. So since that is the case, this is actually greater than or equal to the integration 0 to 1 u square. And what this basically implies, this implies that lambda has to be greater than or equal to 1. So we know that if there's any eigenvalue, it has to be, it has lambda has to be greater than 1. So the eigenvalue has to be less than or equal to 1. So because the eigenvalue we have taken to be 1 by lambda. So for lambda equal to 1, our equation is nothing but minus u dash plus u equal to u, and that is nothing but minus u double dash equal to 0. It's like ux will have some form of a plus bx, but we can see that we need u dash 0. So u dash x is nothing but b only, and we want this to be u0 minus u1. So this actually implies nothing but this is nothing but p is equals to u0 minus u1. So u0 is nothing but a minus u1, and u1 is nothing but a plus b. And but this basically implies b is nothing but 0 only. And that is true. So thus we have, and we also need the constant to be anything. So use ux equal to a is the eigenvector corresponding to lambda equal to 1. So now we have to consider the case when my lambda is greater than 1. So again, the problem is nothing but a second order linear ODE and that one can solve. So after trying to solve the problem, we can see that if we set alpha to be root lambda minus 1, we reduce, because it's a linear ODE, we can isolate an auxiliary equation and solve this. We reduce that UX has to be a cos alpha x plus b sine alpha x. And to satisfy boundary condition, we need to impose b alpha a minus capital A cos alpha minus beta b sine alpha, again minus a alpha sine alpha plus b alpha cos alpha, a minus a cos alpha minus b sine alpha. So it's like when we put conditions, we will reduce these conditions and this system. So this system is actually has a solution if and only if we see price of 1 minus cos alpha plus alpha sine alpha equal to 0. So we just consider the coefficient in one term in A and B terms and then make the matrix. So we will end up with this thing that we have to this thing to be 0. And this is 0 if and only if actually we have sine of alpha by 2b 0. Okay, moving on. We are now, let's see another question based on another operator with like eventually we'll see that like how we can able to find the eigenvalues and do the same set of techniques, but again in another ODE. So the question 3 goes like, consider the problem minus u double dash plus u equal to f on 0 1, u0 equals to u1, and u dash 1 minus u dash 0 equal to k, where k belongs to R and fx are given. So the thing, the problem, the solution. So we are interested in first this problem. So first we have to find the weak formulation of problem 1. Let's name this V1 only. So somehow we have to associate, like we have to this both boundary value conditions incorporated in our V formulation. We start with let U be a classical solution. So if we have U to be a classical solution, I multiply with the V being a test function, and we will see what we are like getting and integrate over the interval. It's like 0 to 1 minus U double dash V plus UV equal to integration 0 to 1 of FV for all V in H1 0 1. So at least we need H1 space to define the U and U dash and to have both of them to be integrable. Next, we use integration of parts to reduce that is nothing but integration 0 to 1 U dash V dash minus U dash V, and we have that at 1 at 0 UV integration 0 to 1 into integration 0 to 1 FV. And this is actually nothing but integration 0 to 1 U dash V dash minus U dash 1 V1 plus U dash 0 V0 plus integration 0 to 1 UV equal to integration 0 to 1 FV. So one thing which we are interested in is like this this U0 and U1 to be equal. So this is somehow we're not able to get if we, because in the, if we try to get free formulation, we're only able to handle this U dash 1 and U dash 0. So somehow we have to incorporate this U1 and U0 to be in the space itself. So we take V, because all those V in H1 0 1 such that V0 is nothing but equal to V1. So we're not able to handle this with just the formulation. So this is we have to extra add on. And then once that is there, so we have integration 0 to 1 U dash V dash plus integration 0 to 1 UV plus now U1 and V1 and V0 equal. So this is V0 minus U dash 1 plus U dash 0 equal to integration 0 to 1 FV. The next thing which we want is this U dash minus U dash 1 minus U dash 0 equal to K, something K. So something I have to add something K times V0 something, so that when my V is, if I've taken H01, so I'm able to get an inequality of U in H2 sense, and then V I am able to remove all the integral term, and ultimately I left with this V0 times minus U dash 1 plus U dash 0 term. But I have to show this term to be equal to K. So I think if we add around K times V0, we'll get the required uh, inequality. So it's like not mine. So not K, minus K will be here. In fact, this whole thing is actually K only. Sorry, minus K. So this whole can be written as now 0 to 1 U dash V dash plus integration 0 to 1 UV integration 0 to 1 FV plus K times V0. So how we define? So we can take AUV to be this thing, integration 0 to 1 U dash V dash plus UV then the weak formulation is U belongs to V, and AUV is equal to nothing but integration 0 to 1 FV plus K times V naught for all V in capital V. So this is a weak formulation. So next we'll show the second part. Show that the weak solution U belongs to H201 and satisfies 1. Well, before finding the weak solution, actually you have to show the existence. So let's write the existence first. So the question 2 is show that for every F in L201 and every K in R, there exists a unique weak solution U belonging to H101 of 1, and also what is the corresponding minimization problem. So clearly this AUV which we have defined is integration 0 to 1 U dash V dash plus integration 0 to 1 UV. So AUV is a bilinear form on H101, in fact on V as well, and candidate and coercive follows directly. Thus by Lax polygram. In fact, the right hand side is again a continuous linear function. Thus by Lax polygram. There exists a unique weak solution U belonging to V, and the corresponding minimization problem is so however it is half of AUV minus on the right whatever we have in the right hand side. So it's like 0 to 1 F times V minus K times V0. This is nothing but minimize V over V. We also have to minimize V over V. A E A V over V. So this is nothing but half times integration 0 to 1 v dash square plus v square minus integration 0 to 1 f v minus k times v0. So next part we will show that the weak solution is show that the weak solution U belongs to H2O 01 and satisfies 1. So since we have this thing here, we have for any V in H0 when I, uh, basically integration 0 to 1 U dash V dash plus integration 0 to 1 UV integration equal to 0 to 1 FV. So like at the end, again the integrations are well defined when my V is in H0 1 and U is actually a solution. So these integrals are making sense. And once and the K times V0 vanishes because V lies in the H0 1 I. And once that we have, this is actually nothing but integration 0 to 1 U dash V dash integration 0 to 1 F minus U times V. This holds again for any H0 1 I, and this actually will imply that U dash is in nothing but H101, and this again determines U is in nothing but H201. So the same technique we used. Finally, part 5, part 4. So take k equal to 0. Consider the operator T from L201 to L201 defined by TF is nothing but equal to U. Check that T is a self-adjoint compact operator. Compute the eigenvalues of T. So once K is 0, it's like the basic problem. And this self-adjoint and compact is actually a direct consequence, and one can evaluate it's not that tough. So it is easy to check that T is compact and self-adjoint. So let lambda k, which I'm taking equal to 1 upon mu k, be the eigenvalue of t, then basically we have this thing, minus u double dash plus u equal to mu k u almost everywhere on 0, 1, and u1 equal to u0, and u dash 1 is nothing but equal to u dash 0 because k is 0 here. And again, if we see that this AUU is nothing but the integration of mu k integration u square, and that is again I know greater than equal to integration of 0 to 1 u square, because AU is nothing but integration u square plus integration of mod u dash square. So this is, we have this thing, and this actually implies mu k has to be greater than equal to 1. And again, with whenever my uk is 1, we have u equal to 1 to be eigenvalue. This implies u constant 1 is the corresponding eigenvector. And when my mu k is actually greater than 1, then again it's a again a linear ODE. Then u is actually given by ux equal to a sine square root of mu k minus 1 times x plus b times cos of square root of mu k minus 1 x, and where square root of mu k minus 1, they have to be actually uh, equal to 2 pi k, for k equal to 0, 1, and so on. Because at the end it's a sum liability problem, and that has actually solution in this type of form only. So this one can reduce, and I leave it to you guys to reduce these things. And with that, I end my session today. Thank you.